Good afternoon. My name is Todd Elwood. I'm with AISC, and I want to thank you for attending our Staggered Truss session today. I'd like to introduce both of our presenters. They're both Johns, one from my region and the other one from Nashville. John Beyer, who's going to be the second speaker today, is from Shelley Metz, Bauman and Hawk in Columbus, Ohio. And our first speaker today is going to be John Kennedy with Structural Affiliates. Both have done Staggered Truss projects. They're both very interesting projects that we're going to learn about today. One was in a very urban setting of downtown Chicago, and then the second project is much more in a rural area of Ohio with a lot of very interesting site conditions and other detail aspects to it. So with that, I'd like to introduce our first speaker, John Kennedy.
Thank you, Todd. Welcome, everybody. Thanks for coming. We're talking today about staggered truss systems, and the presentation today is going to highlight two projects that have been completed by John Beyer and myself, but also I think it's a good overall symposium of the staggered truss system. So we have a lot to cover in an hour, but to give you a quick overview of the presentation, we're going to introduce each individual project to you and talk about some of the unique features of both. And we'll talk about the staggered truss structural system as a whole, and we've kind of broken it down roughly into three components. First, from a design standpoint, which might be of benefit to the engineers in the room. I would point out the graphic is the AISC Design Guide 14, which is a great resource if you're not that familiar with the system. I've read it all, and it has a lot of good information in it. And if you're an AISC member, I think you can download it for free. And also, we'll talk about fabrication and also erection, and some of John's slides are going to get a lot into the erection sequencing and so forth. Along the way, we're going to give references to the individual projects and tie it all together. And then finally, we'll talk about some of the lessons learned from either project, but also talk about some of the benefits of the staggered truss system as a whole. So the project that I worked on is a Staybridge Suites development in Chicago, Illinois. It's right downtown in the River North area for those of you who know Chicago. It was actually the first staggered truss in Chicago, so that was exciting for all parties. It's 14 steel floors over 4 concrete parking levels, 186 feet total height. The typical tower footprint was 190 by 60, and our 10 feet was our typical floor-to-floor. And I would mention that is one of the benefits of the system. It's meant to be a low floor-to-floor structural system. So some of the unique features of Staybridge, first of all, it was a staggered truss tower over a post-tension concrete parking structure, so there were some unique interactions with the steel at the concrete levels that we'll get into a little bit later. But one of them is we did have composite columns for portions of the building. Because it was a parking garage, we were constrained with some of the column dimensions due to traffic circulation and parking space layout and so forth. So the solution from transferring the axial load in the steel columns to the concrete columns was to encase them for a story or two to transfer the axial load, which was worked out to be a good solution. It was a staggered building in 2 directions, actually, and as a quick aside, I will point out that the whole way this project came to fruition was in and of itself somewhat unique. We were actually brought on board before the architect. AISC Solution Center had met with the owner and sort of pitched the idea of the staggered truss system, and he got excited about it. And then AISC actually referred him to our company, and we took the design a little bit further in order to get a fabricator some pricing information. And so whenever you get a structural engineer laying out the building, you usually end up with a perfect rectangle. And so that's an isometric of our first study of this project. But then shortly thereafter, a very renowned architect from Chicago was brought on board, and it was also their first staggered truss as well. So they wanted to celebrate the structure, so their big idea was to stagger the building, which is shown here in the rendering. And you can see this 5-story mass that sort of Jengas out from the rest of the building. It's also inset on either end to expose the steel trusses on both sides. So we actually had to come up with some pretty unique and innovative structural solutions. In this middle area, we ended up developing truss action in 2 directions and some other things, and we ended up with cantilever trusses and so forth. But while it's a far cry from a perfect rectangle, it's also a beautiful aesthetic structure, so it was very exciting for us. There are some insets you can see in the middle of the rendering here, which pose some challenges for our diaphragm design, which we'll get into a little bit later. And we actually were able to sneak in some brace frames behind elevator shafts and so forth for the lateral load resistance in the lawn direction. It's somewhat atypical for a staggered truss. Typically the trusses are going to frame into the web of the column, and in the lawn direction of the building you have rigid moment frames to resist lateral loads. But We were able to avoid the more expensive MoMA connections and use brace frames in the long direction. And finally, it was a very urban site. There's very limited, if not probably next to zero, laydown area. And here's a picture. You can see that the trucks will come out with 2 trusses on them, and the crane would just lift the truss right off the truck and erect it in the air. So, and that's again another one of the benefits of the staggered truss system. Everything's prefabricated, so the trucks can come out on site, and you lift the trusses or the planks directly off the truck and onto the building. Before we go any further, I'd like to turn it over to John and have him introduce his part of the building to you, and then we'll get into the crux of the presentation.
Thanks, John. As you're going to see, these projects are kind of tailored to construction that repeats itself. Ours was a dorm building, and it was for Hocking College, which is in southern Ohio. It was a very rural site, and we had dorms that the rooms were repeating, so you had a double loaded corridor with rooms on either side of a middle corridor or central corridor. So you'll notice that the form of both of our buildings is somewhat rectangular. They're very long and skinny in the one direction. The rural setting presented challenges just from an access standpoint. The college was right off of a highway, but it was back down a winding road, so there was access with getting pieces back to the site. In addition, the building footprint was held very close to the natural landscape, so that the trees were up alongside of each building very close, and so that had to be paid close attention to during the erection. Our building also had a 10-foot typical floor-to-floor. We had a hill on the site. We kept looking over at the flat plains of this site and of the college campus, and we said, can we just put the building over there on flat ground? And they said, no, we really want it right here in the center of our campus. And it was a very hilly site. Our buildings started at about 2 to 3 stories. We had 2 buildings that were almost identical. They stepped up the hill a little differently. So on the one building we had two stories here at the top, and then they worked their way down to seven stories in the front, and the other building was 3 stories in the back, and then also came up to 7 stories in the front. Each building was about 45,000 square feet. Each building had 200 beds, so we were adding 400 beds to this campus. You can see here, this is an architectural floor plan. This is where the truss is being represented. It's a story-deep truss, and John's going to get a little bit into the design and the geometry of the staggered truss, but you have a story-deep truss on every other floor on the column line. So here's a story-deep truss, and then you skip a bay, and then there's another story-deep truss. So those are represented in the architectural drawings, and it's very important early on to coordinate that with the architect of where you have trusses and where you don't. Our bay geometry, we were 24'8" in this direction, and then our truss span was about 48 feet 2. We did have 2 jogs in the building where we picked up an extra 6 feet of length, so that's the 54 feet 2. Our floor system was an 8-inch precast system. We did have a 2-inch topping slab on our precast, as opposed to John's going to talk a little bit about their system was an untopped system. So we had a 2-inch topping that went on top of the precast as the final floor, and in our job the floors were exposed in the finished structure. Some of the unique features of our project. Again, the site was one of the big challenges. You can see the natural grade of the site made its way from zero, and it came up about 40 to 50 feet in the back of the building. So we were trying to nestle these 2 buildings into the hill. A second thing that came up during the geotechnical report was a underground mine, and it was an abandoned coal mine that had been mined back in the 20s. And you can see here, this upper right picture it's an old coal mining map, and what we had on the site were 2 outcroppings. And then they discovered these maps, and they had to line up the outcroppings, and we discovered through the soil borings that there was actually a 10-foot void under parts of our site where this coal mine had been mined out. And so to deal with this void, we came in before the project, and we drilled a series of holes, and these were covered on civil drawings, and they pumped the mine full of grout. And so that solved a couple things. It kept the danger of subsidence from ever occurring so that this mine wouldn't collapse. The second thing it did is it allowed us to take deep foundations down through the mine and take them through the mine in a substance that could be drilled through and get them to a sustaining bearing strata. here you can see we had a pile and lagging wall because of the way the buildings were stepping up the hill, and there you can see where that coal seam has been exposed, and that was an area where it hadn't been mined, but as you made your way back into the hill further, you hit the void. We had tight boundaries, as I mentioned before. Here you can see you're standing in one of the buildings looking over at the second building, and in between the two buildings the natural trees were kept, and right here is where our pile and lagging wall was that you saw in the previous photo. As I also mentioned, we took drilled piers down through the grouted mine, and we took them down below the grouted mine, and the front of our building in front of the pile and lagging wall sat on spread footing, so we did have a combined foundation system. We had some expansive soils on site, and we also had some moisture and water issues, so the entire building ended up sitting on crawl spaces. This was an advantage of the staggered truss system. It allowed us to not put any foundations in the middle of the building, and so all of our foundations were at the exterior walls, and because of the way the buildings were stepping down the hill, we used our exterior foundation walls as deep grade beams, and then put piers at each column line with a drilled pier as the foundation at each column. So it allowed us to really reduce the number of interior foundations that we had for the buildings, which was a big advantage of the system. And now I'm going to turn it over to John, and he's going to start by going through some of the design basics, and then into the fabrication and erection, and then I'm going to kind of repeat the sequence.
Okay, so continuing with staggered truss design basics, some of these concepts are somewhat fundamental to truss design, and in the interest of time we'll go through them somewhat quickly, but to highlight a few things, the most common configuration is a Pratt truss, such that the diagonals, your longer diagonal members, are going to be in tension. There's a Vieira and deal panel at the corridor, which a Vieira and deal panel in a truss wants to be in the center of the truss. So that's why the staggered truss system works the best for dormitories, hotels, apartment complexes, anything with modular unit dwellings that have a long centrally running corridor down the middle. The number of panels is a design consideration, and it's pretty much driven by the span length of the truss and your Vieira and deal panel location and so forth. But a common economical design has your diagonal members at 45 to 60 degrees with the horizontal. And the trusses stagger in the traditional checkerboard arrangement. The trusses stagger from floor to floor on adjacent column lines, so that your plank spans from the top chord of one truss to the bottom chord of the next to the top chord of the next, and so on. There are modified arrangements of the staggered truss system that are somewhat documented. We used one of them on our Staybridge project, actually, but the traditional checkerboard arrangement is described by that. Truss connections are an important consideration, and what I do want to point out here is you want to try to keep your stress ratios for the diagonal members at about 80%, 0.8 or 0.85, and that's due to when you get into some of the connection design, your shear lag equations and your effective area reductions and so forth. You want to make sure that you can achieve a workable connection. So keeping your stress ratios below 0.8 or so on the diagonal members is important. And like any project, there's going to be special conditions that we'll talk about on the next slide. Here's a typical truss elevation from the Staybridge project, and there are some unique features. The first two, posts and hangers, are common in most of the staggered trusses that I've seen. You can see at the top here, when there's not a truss at the top level, we post up from the panel points to frame out the penthouse level. Also, their fourth floor right here was lobby space, and so in order to avoid interior columns in their lobby, we hung a beam from the panel point of the truss above. Those are common elements in most staggered trusses. What might not be common in a traditional staggered truss are cantilever trusses, and again, the building offsets kind of drove us to this solution. Instead of having the columns at the very exterior of the building, we ended up bringing them inboard a certain amount so that the columns could be continuous, and then we could avoid expensive transfer levels here and here. And so as a byproduct of that, to frame out the exterior, we ended up cantilevering trusses off of the main building columns. Shear transfer at the base is an important consideration. You can see here, this was a typical brace panel that we had at every truss location to get the load from the staggered truss tower down to the concrete levels. And from the concrete levels, we had shear walls that were located and designed to transfer the lateral forces to the foundation. And then finally, the transition from steel to concrete. On the Staybridge project, it was somewhat unique. We were able to align the main column grids. Because there were only 2 main column lines in the tower, we were able to easily align them with the concrete parking levels, and so that transition was somewhat eased. Even if you carry the staggered truss all the way down to the foundation, there's still transfer of forces from steel to concrete there. But continuing with some of the design basics, the lateral load resisting system, this is just a very generic floor plan of a traditional checkerboard staggered truss. Traditionally, you use the trusses in the short direction to resist lateral loads, which actually is great. For one thing, the trusses are very stiff and drift can be kept to a minimum. Also, by the time you design the trusses for gravity loads, you can essentially get your lateral load resistance for free. Typically, there are rigid frames in the long direction of the building, but other systems are possible. For example, on the Staybridge project, we were able to use brace frames. And as far as the floor system goes, hollow core plank is the most common, but other systems are possible. I know that we recently did a study in the last year or so for a fabricator, and we were looking at using a long span deep deck that would span 28 feet between the trusses and look at using a poured concrete floor. But like I said, hollow core plank is the most common, and that was the floor system for both the projects of John and I. And so a few other things to think about, and you have it pretty well licked. We're not going to talk about all of this, and some of it is also pretty typical for any project, but for staggered trusses, some of the things we are going to highlight are bracing, diaphragm design, some plank issues with floor penetrations and blockouts and so forth, and also fire protection of the staggered trusses. So as you detail your staggered truss project, there are a few things to consider. One of them being the flange width of your truss cords. You want to make sure it's wide enough. This is another generic cross section through a truss. You can see that you're going to have plank bearing on either side. So maybe your plank needs 2 inches of bearing minimum for support, and you also typically would have a Nelson studs and maybe some reinforcing in that grouted joint over the truss cord. I think for our project that grouted joint was 4 inches. So when you couple that with the bearing requirements of the plank, you want to make sure that your truss cord flanges are at least 8 inches. 10 or 12 inches might be even more ideal. Another thing to think about is the gusset plates, especially on the bottom cord. Your gusset plates are going to be larger than a traditional brace frame or something, for example. The reason for this is you have to have enough room for the planks to come up on either side, and so if you have an 8-inch or 10-inch plank, and you might want to provide 2 inches of clearance so they can set the planks, you can end up with a gusset plate that's very large, and your pre-composite loads might drive the design of the whipboard buckling of that gusset plate due to its length. So the size of the gusset plates is an important consideration. Grouting the joints, this is especially true if you do use an untop plank system. We had an untop plank system on the Staybridge project, and so thus we had to transfer our shear forces in the diaphragm through these grouted joints in the long direction and keyways and so forth. But the full depth grouting of those joints does become critical. It might be something you even want to specify special inspections for. Connections are an important consideration. You're going to have a fairly shallow truss cord depth, and there's a lot of load coming in these connections. So a common connection involves double clip angles and so forth for the additional capacity. And finally, seismic detailing. Both our projects were actually wind controlled, and there are some irregularities and so forth with the system that might preclude the applicability of the staggered truss in a high seismic region. I think it can be done. The AISC design guide does address some seismic detailing requirements, and I think the plastic hinge locations are typically detailed in the Viera and Dio panel and so forth. I think it has been done successfully in the past, but we're not going to get into it too much in this presentation because, like I said, our 2 buildings were wind-driven. So as you go through the design, there are some important things that you want to go over with the architect. Obviously, the truss locations are located within the demising walls, and so you want to make sure that your wall width is wide enough to accommodate the truss with your architect. The floor-to-floor heights are one of the most important parameters to select early on in the design, obviously. Corridor location and egress, it really needs to be stressed to the architect that your corridor has to be in the middle, so you can't let the architect do anything fancy and run the corridor out to the exterior of the building and so forth. The edge condition for cladding support, this was, we ran into part of this on the Staybridge project as well. You're going to have plank, because the planks are precast elements and as opposed to a poured in place floor, you're going to have blockouts in the planks at your exterior column locations and gusset plates at your exterior trusses, and so you're going to end up with a void of sorts that you need to come up with some structural detail to support the exterior wall or whatever is needed for the architectural facade at these precast blockouts. And the use of finished plank surfaces for flooring materials and exposed ceiling. One of the benefits of using precast plank is, and this was done on Staybridge, the architect simply specified a blown popcorn finish on the underside of the planks, and so in the rooms you can use the underside of the planks as your exposed ceiling, and that saves a lot of soffit materials and so forth. And also, if you use an untopped plank, your finished plank's top surface is also going to be used for direct application of flooring materials. You need to make sure that you can coordinate your camber requirements and tolerances with your precast supplier to make sure it can be done. But both the top and bottom surfaces can be used for those architectural features. And finally, fire protection. Fire protection is normally specified. It's normally in the architect's court to work through it. But as engineers, I think it's important to provide some guidance with them, especially with a unique system like the Staggered Truss. And to continue to that end, the Design Guide 19 actually has a section devoted to Staggered Truss protection. And it might because our office actually co-authored the Design Guide. And you can see within that section there are UL assemblies that can be specified for the Staggered Truss system itself. There's basically two ways to do it. You can protect the trusses via like a wall envelope protection, or also a spray applied fire resisting material, or a combination thereof. On the Staybridge project, we actually did use a combination. The steel trusses were protected via a wall envelope assembly, and that we were able to achieve a 3-hour rating with the trusses just with wall enclosure. The columns, however, needed to maintain a 4-hour rating, and so what they ended up doing was spraying the columns and then using the wall envelope protection for the trusses. Also, an important design consideration is mechanical, electrical, and plumbing coordination. There are a bunch of things to think about as the design progresses, and not the least of which are floor penetrations. Frame traces in a mid-rise building, your frame traces might be somewhat large, and the location and the support for your planks and so forth needs to be thought about. Again, one of the advantages of the Staggered Truss system is maintaining a low floor-to-floor height, and so having header beams and so forth to frame out chases is something that needs to be worked through early. Also, penetrations through the bathrooms. Your precast planks are only 4 feet wide, and so most of the plumbing penetrations, for example, are gonna come in at the bathroom, and you got to make sure that the plumber's not going to put 7 penetrations through a 4-foot wide plank, and things like that. So those are some things to think about on the MEP side. Also, equipment support. You'll undoubtedly have heavy air handler units on the roof, and if you have a plank that's going a long way, maybe it's not good enough to support it. Maybe you need to have steel support for your mechanical units. And then you're also cutting into your ceiling heights and so forth or whatever at that level. So that's also an important consideration. And then finally, the above ceiling utilities. Traditionally, in a Staggered Truss building, all the distribution systems are going to run down the corridor. So, and in order to maintain code-required ceiling heights or an owner-driven ceiling height in the corridor, you really need to know early how much with the design of the MEP trades, and this might also influence the floor-to-floor heights. We ran into somewhat of a challenge at Staybridge, and it was mostly due. The design of the mechanical, electrical, and plumbing trades were actually not a contracted part of the design team. They were design build subs of the general contractor, and they also changed, a portion of the way through the design. So after our structure, we submitted for an early permit and so forth, and after we had addressed all of our comments, the electrical engineer came back, and there was some challenges fitting all of his electrical conduit within the ceiling height of the corridor if he was to run it beneath the steel. So he wanted to run it in the plane of the steel, which meant web penetrations and maybe some expensive reinforcing details and so forth. We worked with the fabricator on the solution, and it ended up being a fairly good one. We allowed the conduit to run in the plane of the steel, and we ended up with some 5-inch diameter circular penetrations through the truss cords where they were required. And because they were circular, and when we looked at the forces, we were able to do it without the expensive expensive fabrication costs associated with reinforcing the web with angles and plates and so forth. So that was a good solution. Here's a picture under construction that I took looking down the corridor. We didn't have to do it everywhere on this particular floor. It was through most of the trusses, actually. We did it where we had to, but and the final product, as they were roughing in the MEP, is shown here. So that was a good solution to a problem that crept up. Diaphragm design, I want to touch on this because diaphragm design is tantamount to the success of any staggered truss. Primarily because you have an atypical lateral load path compared to a conventionally framed steel structure. And what I mean by that is the vertical irregularity associated with the system. You can see, if I get my laser pointer to work, in this little isometric, your lateral forces will come in at the top chord of this truss right here and transfer through the web members and into the bottom chord. Into the bottom chord of the truss. Now once it gets there, there's no vertical resisting element below it, so the lateral load path, the lateral forces have to be transferred through the diaphragm to the adjacent trusses on each side, one bay over. So because of that irregularity, it's important to pay attention to the design of your diaphragms. A rigid diaphragm assumption is usually valid due to the nature of the floor system. Usually you'll have some kind of concrete floor and a rigid diaphragm usually works. But in reality, all diaphragms are between rigid and flexible in some capacity. So it's important to draw shear moment diagrams of your diaphragms for the building. We actually did shear moment diagrams for every story in both directions. And also for diaphragm integrity, well-designed and well-detailed diaphragm chords are important, especially for a unique lateral load system like the staggered truss. And also the selection of the floor system should consider diaphragm design, and it might require investigation early in the project. I know that a lot of the experienced engineers might be able to look at a building and know that the diaphragm will work, or maybe you check it later before it goes to permitting or something. But you know, you want to make sure, especially if you're using something like an untop plating system like we did and so forth, you want to make sure that you're going to have enough diaphragm depth and so forth and connection capability to transfer the required forces. So you might want to look at it early. Here's a example of our shear diagram for one of the middle floors of the Staybridge project. You can see the white distributed load. It's not very much. It's actually the lateral load that just comes in at the one floor. However, the white arrows are the actions imposed from the trusses above the floor, and the red arrows represent the reactions from the trusses below the floor. So you can see how the shear diaphragm is going to look for that assembly. And once you have your shear diagram drawn and you understand your forces, you can calculate your shear flow pretty easily and use some method of transfer mechanism to transfer the required forces. For our project, we used grata joints and keyways and shear studs and a multitude of each. We also had embed plates. Those were primarily for erection stability, but they could also transfer lateral loads, and probably a good portion of them actually, but it's a good idea to have belts and suspenders, I think, especially for something as critical as the diaphragm in a staggered truss. And then integrating the shear diagram, this is the moment diagram for the same floor, and the moment diaphragm will, by dividing by the diaphragm depth, will give you your chord forces, so you can design and detail chord forces. You can see our diaphragm chords were located here at the extent of the building primarily, but you can see where the insets in the building shortened up our diaphragm, and so what we had to do was put another diaphragm chord along the inset and carry it over a couple of bays so that the continuity could be maintained. And I will say that one of the unique parts of this diaphragm chord is this is where the hotel rooms are, and so they wanted to avoid having a bulkhead or something because the underside of the planks was going to be the ceiling. So what we came up with, the details of our diaphragm chords are, we used a tube section along the very perimeter, and you can see the attachment has to be thought through. All planks are going to be cambered because of the pre-stressed tendons, and so your steel, beyond a little bit of natural mill camber, is primarily not. So what we ended up doing was putting an embed plate in the underside of the plank here, and then welding some vertical plates to the side of the tube, but a sufficient number of connections to transfer the chord forces into our diaphragm chord elements. And for the diaphragm chords at the inset that we looked at earlier, our solution was to use an upset WT section, and the reason for this is because the underside of this planks right here were going to be the exposed ceiling, and so to avoid a bulkhead, the only protrusion from the ceiling, if you will, is the thickness of the WT. So that ended up being a good solution for our diaphragm chord. From a fabrication standpoint, your fabricator might have a preference for connection design, and then from the discussion we just heard, maybe the fabricator is designing the connections. Section availability may be an issue. Probably not so much in a large city or a big fabricator, but you know, in a very rural environment and a small local fabricator, maybe section availability is something that you want to discuss early on. Truss design, weight optimization versus truss repetition. There's been some debate that I've read and heard. One school of thought is it's an easy thing to do to design one truss, you know, your worst case truss, if you will, and then put it everywhere. And you're penalized somewhat on the weight of the trusses, but your fabricator can also set up a jig and maintain the same sections all the way through. And also from a connection standpoint, your workable gauges and so forth are maintained at your truss cords. The opposing school of thought is to not do that and to just optimize the trusses for weight, which is what we did on Staybridge. So as you get the trusses on the higher floors are lighter than the trusses on the lower floors and so forth. The fabricator should also consider erection. Maybe he is the erector. And also a consultation of the fabricator early on, as early as you can, especially for a unique system like this. You can get a lot of benefits and a lot of these questions answered by getting with them at an early stage in the design. And from a construction standpoint, the sequencing of erection is very important. And an urban versus greenfield site should also be considered. Both of us had the opposing sides of this. I mean, for us, the contractor had to you know, keep a pretty stringent schedule and have the trucks deliver 2 trusses and lift both of them up at the crane at the same time, and then the truck left and so forth. So there's a lot of scheduling and some sequencing that had to be considered on the construction side. It's advantageous for the same erector to erect both the trusses and the plank for a multitude of reasons, and depending on the situation, it might not always be possible. It was for our project, and I think it was also for John's project. But there are many advantages to it because of the close interaction between the planks and the trusses. The temporary bracing of trusses and columns is also very important on the construction side. Sometimes this is a means and methods issue left up to the contractor, but as engineers, it's also important to communicate as much information you know, as you can to them, because you know, the engineers might possess unique knowledge of structural behavior that the contractor won't. As a quick anecdote, on the Staybridge project, we had embed plates in the plank to provide temporary erection stability for the trusses. And when I was out there on site, I went out there and they had erected almost a whole floor of precast plank, and I walked underneath the trusses and not a single embed plate was welded down. So I asked the contractor, and the contractor said, "Oh, well, we're going to erect 3 floors of plank and then have a welder blow through and do them all at once." So that sort of defeats the purpose of using them for erection stability. So after pointing that out and explaining, you know, buckling and so forth, we got them to weld the embed plates as they go. And with that, I'm going to turn it over to John's portion of the presentation. He's going to go back through some of his experiences with his project.
Again, I'm just going to walk through a few design things first, and then towards the erection is my part of the presentation is a little longer in that end due to the fact that we were directly involved in the erection sequence on our project. So to start with some of the design forces and talk about axial loads first, I have a couple sections of one of the column lines of the building and just show you some of the forces that are going on so you can have a feel a little bit of what typical forces are. This is under gravity loads, just under axial loads. You can see the loads coming down the columns. They're getting bigger as you come down. And one of the advantages, and John mentioned this, is that with the Pratt design, you're going to end up with your diagonals under axial loads. The diagonals are going to be in tension, and your verticals are going to be in compression. And what this does is it allows you to be a little bit creative in choosing your shapes for the diagonals. The design guide talks a little bit about the option of using double channels for the diagonals being good in tension, and then using tubes for your verticals since you're mostly in compression. Now, you have to also look at your lateral loads because, as we'll see in the next slides, they're going to have a reversal effect, and so you have to look at the load combinations and see what the net result are in the members. But under gravity loads, these are the kind of forces you'd see. From a bending standpoint, when I analyzed our project, I broke it into two kind of load cases for dead load. The first case is when you put the precast on, and it's a pre-composite type of load. So everything's acting independently. The steel frame is acting on its own. And when you look at that lower picture on the left there, that's a top chord of a truss with that first diagonal coming up, and it ends up being this connection right here. And by looking at that connection, you can really see the stiffness in that connection. And once that thing's detailed out, it's going to be a very stiff connection. And so when we analyze it, I analyze that as a fixed moment connection. And so it's dialing moments into the column. So what you don't see here is you see a strong axis bending in that top chord, and it's dialing that moment into the column. And in our project in the other direction, we had moment frames. So that column is framed weak axis into the truss. So you're dialing a weak axis moment into the column. It's something to pay attention to, just to realize that when you do your column design, you could potentially have weak axis moments coming into your column under these initial gravity loads. The second case under dead loads is after you put the plank on, you grout the plank in, and now you've got a composite system, and that concrete plank is going to act when the truss wants to deflect and this top chord wants to go into compression. You now have a composite flange with that precast. So your deflections and your trusses go down, and so we model that top chord connection now as a pin connection. And by superposition, take that into your load combinations and then design the members from there. This is the shear diagram. Nothing special here, but want to show it to you just so you can see what the chord members are doing with that transfer of shear. Because remember that the plank is loading each of those chord members between the panel points, so you are getting loads applied to those chords. Moving to lateral loads a little bit, show you the same thing with the axial loads now, and this is due to wind load, and we have a wind load coming in from the left. So it's trying to take this whole frame and it's trying to tip it over so that the set of columns on the right go into compression and the set of columns on the left go into tension, again due to simply lateral loads. You can see here where we start to get the reversals in the diagonals. In some of your diagonals are going into compression and some are going into tension. So again, you need to look at those load combinations and see what the net forces are to design the truss members. Bending, again under lateral loads, you start getting reversals because those trusses are the members taking the lateral load, so you'll see positive and negative bending in your chords. And then in our project, in the long direction of the building, we use moment frames, as I mentioned. And the way our building was stepping down the hill, as we stepped down, we started shedding our lateral loads into the concrete walls as we got down the building. So you see that our lateral frames, which are these three interior bays, start to drop off, and we don't have any more moment frames once we get low on the building. But we took the middle three bays of the building and we made those into moment frames, and so that's what you're seeing there is the moment diagram of those spandrel beams that are running along the perimeter of the building. In terms of getting into the detailing, and we've mentioned this, but just to show you the picture, this picture on the left, this is a bottom chord, and this gap here is that gap that you saw to be able to slide the precast in. So on our job, it was 8-inch precast, and then we left a 2-inch gap. So you're looking at least a 10-inch gap there on the bottom, and also just the magnitude of the size of those gusset plates. One thing to keep an eye on is this isn't a Varendale panel here, but on your Varendale panel in your corridor, you want to make sure as an engineer you specify that gusset plate can only stick out so far from that vertical, or else you're going to end up with a gusset plate in your corridor. So something to just keep an eye on in that middle panel is to make sure your gusset plates don't end up popping out of a wall. Another question that comes up that has to be coordinated with the erector and the fabricator is how are the trusses going to be erected? Are they going to be part of the truss, or are they going to be independent columns that then the trusses are slid down between columns? On the right there you can see that those two columns are being spliced. The columns are being spliced at each floor, so your columns end up being part of the truss itself. On our project, it was not done like that. The columns were framed up a couple stories and then spliced every 2 to 3 stories, and then the columns, the way ours was set up, the columns were slid down through that web. So it was important to make sure that those splices allowed the columns to be inserted and installed between those webs. And you can see here too, this was a column splice, our typical column splice. On our project, they were designed for the full moment capacity and shear capacity of the column. It can be done either way. It depends on how much coordination wants to be done with the engineer. You can tailor those splice connections to be at specific places on the column, and then the moments and the shears have to be given to the detailer, the designer, for those splices. From a fabrication standpoint, storage considerations too, remember the fabricator is creating these large assemblies, and if there's going to be a lag, in our case, the initial plan was take these things straight from fabrication out and start erection. Well, there was a delay where there was this window of time that had to occur after fabrication was complete to the erection. So the fabricator ended up having to store these large trusses on site or off site for a period of time. And so remember that these assemblies are large. They do take up a lot of space until you get them out to the site. From an erection standpoint, John mentioned the erection sequence a little bit, and in our project we had in our specifications that you had to submit a signed and sealed erection plan, and that was to be done by the fabricator. In our case, the fabricator, the erector was under the fabricator in the contract, and they were required to submit an erection sequence. As it turned out, we became that engineer that helped with the erection sequence. So the first thing we worked with the erector in determining was the erection sequence. So because of the way our buildings stepped down the hill, the thought was to start at the top of the hill where the buildings were the smallest and create a stable mass that we could then erect the rest of the building off of. So we started at the top with that erection sequence 1 and made our way down the hill. There's a great deal of coordination that has to take place during the erection, as John mentioned, because of the weld plates. You're using the precast to brace the steel in the erection. The main goal of the erection sequence is to brace this top cord that's trying to go into compression, and you can see one of the ways we did it here was using pipe braces to go up and brace that, and that pipe brace is going down into precast, then that lateral load has to go somewhere. So you have to make sure that the precast that are being used for erection stability are being detailed out at the same time as the steel is being erected. So that's something to coordinate. In our case, the precast supplier was supplying the precast, but the steel erector was actually erecting the precast. So there was a minimal amount of detailing that was done on the precast as well as the steel, and then at a later time the precaster came back and finished the detailing of the precast. Again, I mentioned that the bracing of the top cord is essential in the erection sequences. What I want to do here is on the next slide I'm going to show you an animation, and it's going to kind of step through the basic animation of the building, and I want to go through each step that you're going to see because it moves a little bit fast, and you'll see these steps, and then what you're going to see is the steps just repeat their way through the building. So the first step of the erection is you erect some steel. We erect our columns, our trusses, and then also our spandrel beams to tie the whole frame together. And that was erection sequence 1. We install some temporary X bracing, and that's just some cables and that kind of thing to both plumb the building and then also provide some lateral resistance in this direction because we don't have any of our moment frames installed yet. You'll also see some X bracing here below this truss, and that's due to the fact that we haven't established a diaphragm yet in the short direction of the building, so we can't shed our loads from the bottom of one truss adjacent to the other 2 trusses. So we have to install some X bracing in those locations so we make sure we've got our lateral loads taken care of in both directions. The next thing we do is we come in, and this truss is going to be the first truss that's loaded as we put precast on the bottom cord of this first truss. So what we do is we come in with some cable bracing, and we through an analysis decided that we needed to brace that top cord in one place. So we put cable bracing onto that top cord, and then there's dead men or something to hold that in place. Next step is we go in and we install some precast, and in our case we install it out to that first vertical in the Verandil panel, and at that point if we take the precast any further we're going to hit that diagonal rod. So the next step is we came in with a pipe brace and put a pipe brace going from that top cord down to the precast, and at that point then we can take out that cable bracing and we can run our precast the rest of the way across the bottom cord, and you'll see a second pipe brace is shown up too. So that's the general process. It just simply repeats itself, and the goal is when you get to the end of this, The next goal is how are you going to brace that next truss from the top chord. So you'll see that process repeat itself. So this is going to step through the animation. You'll see the members highlight, and if we could find a mouse, there it is. So here, like I said, the first step is installing that first sequence of steel. And in this one, you're not going to see that temporary bracing in the other direction. We'll go straight to the bracing of that first top chord. And we install the precast across there. We've braced our top chord of that truss. We now move on to the next truss we're going to load, bracing that top chord, and the sequence simply repeats itself. You'll see a couple places where we do some unique bracing. In the next slide here, you see where we've braced across that from that previous diaphragm across to get that next truss we're going to load. So once we finish that first sequence, we now come in and we erect some more steel, the trusses, and the process simply repeats of trying to brace those top chords as we start to load the precast onto the bottom chord. And again, same sequence, just repeats and repeats, and again, we got to get out and get that top chord. You see a few diagonals back here that are going to stay in place, and that's because on our project we had trusses that came in later that were going to provide the permanent bracing for the top chords. So those stay in. The rest of this pipe bracing is pulled after you get most of the precast up. So that's the general sequence of how that building was erected. Again, our buildings are very similar, so both of them were very similar to each other, but because the other building started with 3 floors in the back, it was a little different. From a bracing technique standpoint, you can see those temporary braces that have stayed in place up here. Those are the pipe braces. Very lightly, you can see some of that X bracing that's been installed. And here's a close-up of those pipe braces. We took a drilled anchor and drilled them down into the precast, and then there's a temporary tab that's welded up onto the cord to keep those installed, and then those are pulled. And from a visual standpoint, not a big impact because all this is being covered up. In our case, they were gyp enclosures to get the ratings, so all of this ends up being covered up, and we had a topping slab that any holes created by the drilled anchors were covered. To summarize some of the lessons we learned on the project, and I think that was the topic of the conversation, but John mentioned it a little bit with the notches in the precast. We also ran into the issue with your exterior cladding and also just from a coordination standpoint of where we had our moment frames along the long direction of the building. We had plates and bolts that created those moment connections, so making sure that those were coordinated with the precast supplier. John will talk a little bit about maybe the notches that occur at truss locations where you have the gusset plates at exterior bays of the building. Headed studs, the Nelson studs that you're putting on the cords, you need to make sure you coordinate who's going to put those on and when they're going to be put on. The fabricator likes to put those on in the shop because it's a lot easier to put headed studs on a truss that's sitting in the shop rather than something out in the field. The problem is, do they become a tripping hazard? And that's something that has to be coordinated. It's a lot harder to, maybe with a stud gun, you come in and you can put those in if the gap's been maintained once you have the precast in place. But again, it's easier to do it in the shop if you can. Precast camber, truss camber, the combination of the two. On our job, we did put some camber into our trusses. We also had camber in our precast. So in the middle of a piece of precast that sits in the middle of a truss, you're going to have the combined camber of both of those. So you have to be a little bit careful of your cambers, and in our case, our topping slab was 2 inches, but I think in places it probably got down to a 1/2 inch. So it's something to keep an eye on, and making sure you're coordinated. Also around stair openings where you have a long piece of precast next to a short piece is where you can get into some camber issues. And then, like I said in those last few slides, the importance of the erection sequence, because these buildings are different than the typical steel to erect, it's important to have a plan for an erection sequence. And in our case, one last comment, to expect a crack in the topping along the length of the truss cord. And we had finished floors on this job, and even though we had fiber in the floor and we reinforced down in the precast joints, we still ended up with a crack where those two pieces of precast came and butted into each other. And I think that's just due to you're losing your deflection and you're losing your camber in your precast. So in our job, you really only saw that crack in the corridor, but maybe you come back through and if you want to tool a joint, you have to remember that you're also relying on that that topping, that precast for diaphragm load. So you don't want to create too large of a gap there to transfer lateral loads. And I'm going to let John now go through some of the lessons learned from theirs.
So to conclude our presentation, some of the lessons learned from the Staggered project that we came with is that coordination between the design team. I say lessons learned. Really, it's just things to think about, I guess. I mean, I think lessons learned has somewhat of a stigma associated with it. I mean, we knew a lot of these things as we were going through the design, but these are certainly some things that we wanted to share with all of you. But coordination between the design team is critical, including your mechanical, electrical, and plumbing trades. The floor-to-floor heights, considering all parameters. Some of our cord penetrations might have been avoided if we had early information from the MEP designers. But also, the early involvement of the general contractor, fabricator, and plank supplier is ideal. Especially in this system, the interaction of the steel and the plank is very important, and your fabricator and plank supplier need to be talking to each other and on board early, along with the general contractor. Like I said, it's not always practical if it's a bid project or something of that sort. But I mean, if having them on board early there are a lot of benefits to it. I will say discretionary use of on-top plank systems. We did have an on-top plank system on this project, and we were able to make it work. But as John mentioned, and I mean, every precast plank is going to have camber associated with it. Because we had cantilever trusses on the Staggered project, we didn't have to camber the trusses in the middle as John did. But you're still going to have differential camber, and as he mentioned, especially whenever you have a long 33-foot plank, say adjacent to a 18-foot plank, that'll have different designs. There are methods of mechanically fastening the planks that we went over with the construction team for this, and you also might have to use a floor leveling compound, a gypcrete or something similar. Because also some plank suppliers, I've talked to several plank suppliers that won't produce or won't ship out a carpet direct on top plank. So it's very supplier dependent. So if your plank supplier is not on board early, you have to make sure that once the general contractor is on board, that you communicate to them this is an on-top plank system, and make sure that your precast supplier understands it and so forth. And if you use an on-top plank system, the grouted joints become very critical for shear forces and floor system integrity and so forth. So your shear transfer and your transfer of all your forces needs to be considered if you're going to use that type of system. So there's a lot of things that need to be thought about. With that said, I will say that AIC, I believe, also endorses the use of the on-top plank system. The reason being it eliminates concrete and wet trades after they come out of the ground, essentially. So everything after the foundation elements become just prefabricated trusses and also the precast plank elements, and the grout could be mixed on site and so forth. So you eliminate your concrete sub contractor as they come out of the ground, which can save a lot of time and money. So there is some benefits to using it, but you should use it with caution, I would suggest. Coordination of exterior edge conditions. We ran into this as the design progressed. Because, as I said, and John had a good picture of it on his slide, but there are going to be plank blockouts at certain locations, primarily at the exterior columns, and also we had trusses on our exterior. Some Staggered truss systems use post and beam framing for the last two exterior bays. So the problem somewhat might go away. But if you have a truss, your gusset plates, as we talked about, are going to be very large. And so we had a plank block out that was 4 feet at an exterior truss. And so as you know, what's going to support, if you end up cantilevering the plank over the exterior truss to support the exterior wall, what's going to support it for that 4-foot block out. And we worked with the precaster to develop some solutions to that end on our project, but maybe a bent plate might be a more common or a better detail at the exterior trusses. So if you can stop your precast planks on the inside and then just have a welded bent plate on the exterior with some kind of poured detail, that might be a good solution as well. We had thought about that on Staggered, and it was precluded. The contractor wanted to avoid poured in place concrete details and so forth, and so that's why we ended up going to cantilevering the planks the 1-foot dimension to the exterior wall. But your blockouts and your edge condition support is something to think about. And finally, careful attention to erection sequence, schedule, and delivery in an urban site environment. It's something that might be out of the designer's hands to some extent, but it is something to think about and needs to be considered. With that said, I know we're running out on time. There are a lot of benefits to the system, and that's why the concluding slide that I wanted to end with shares a few of them with you. One of the biggest benefits that in my opinion is the speed of construction. because everything's prefabricating, can be erected quickly. I know of one staggered truss project, I think it was in Arizona, that AISC has presented about before. They erected something like 12 floors of trusses and plank in 19 days or something like that. It was, I mean, there are a lot of benefits to the speed and expeditious construction. With that said, if I know it's right at 4 o'clock. If there are any questions, we'd be happy to field them, or I would also invite you to come up to John and I at any point, you know, the whole week and discuss any of your questions. But if you do have any, we'd be happy to field them now.
Right before that, too, in the back of the room, we have several design guides and other brochures about the Staggered Truss, so be sure to help yourself on your way to the next session. With that, I'll turn it over to questions.
Sir.
You mentioned something about the Staggered Truss to be in two direction and the State Bridge building. Could you please elaborate on that?
It was actually a very complicated detail. The Staggered Truss itself wasn't in two directions. It was truss action developed in two directions. If you can see from the rendering here, the building is inset. These two are exterior columns right here, and so the Staggered Trusses span this direction primarily. But we ended up cantilevering trusses over to frame out this portion of the building, and it's hard to see from the rendering, but there are actually diagonal members going back to the building columns to support this element. So we developed truss action sort of in the long direction of the building as well, just to frame this inset of the structure. Without getting into the details, it was pretty complicated, but that's in a nutshell how it worked. Sir. I mean, in the long direction, in the long direction of the building is I mean, I wouldn't see much need for cantilevering elements. I mean, typically your exterior columns are going to be all along, and you can just frame beams in between them. But you know, I mean, and without knowing, it's somewhat of a general question, but without knowing the specifics, I mean, you know, anything's possible with the right amount of money, as we all say, right? Sir. Lower than it would have been. I remember the fabricator did these studies during his presentation. It was lower than it would have been if it was a traditional composite and like a traditional steel frame structure. I think it was something on the order of 12 PSF or 13 PSF, but I'd have to go back and look. I can't say that with any amount of certainty.
And I don't remember our number offhand.
Do you remember SOC? I can't recall specifically. Yeah.
Do you remember what the cycle time per floor was in your job?
No, I don't. To be honest, on the construction end, we were designing other projects and so forth, and I don't really recall. But I mean, it's not unusual to be able to erect a floor every week or two. I mean, I mean, if everything's well coordinated, it mostly has to deal with how quickly the contractor and how good he is with scheduling and sequencing of everything, getting things on site. But you know, I mean, that's really the limitation. I mean, if you have an 8-bay building, you only have 4 trusses on each floor. So if the columns are attached with 8 crane picks, you have the steel skeleton for 2 floors. And then, you know, I mean, you can see a lot of speed there. I don't remember exactly what the cycle time was though on our project.
And ours originally was very schedule driven from an erection standpoint, and then because it was a dorm, there was a delay in funding. And we missed this 3-month window, and it went to the next year. So the erection became at a very more relaxed pace. But just being out there watching them, I have no doubt that they could get an entire floor framed in a couple days and then go to the next one.
With that being said, thank you very much, and enjoy the next session.
Thank you.